In today's video, we're diving deep into advanced pointer techniques in Zig. We've already explored the powerful concept of pointers, including single-item and many-item pointers, along with their roles in memory management. Now we will cover how to manipulate pointer values directly and the practical applications of conversions between pointers and integer addresses. This session is going to be packed with examples, explanations, and some interesting use cases that will elevate your understanding of pointers in Zig. In this section, we'll see how to convert an integer address into a pointer using Zig's at ptr from int function. Now let's write the following code where we start by declaring a constant eta that simulates a physical memory address. In this example, we use the value 0x1000. We then utilize at ptr from int eta to convert this integer address to a pointer type, specifically a pointer to an i32. It's important to note that this technique allows us to interact with raw memory, but it comes with the critical responsibility of ensuring the address points to a valid memory location. Failing to do so could result in dereferencing an invalid pointer, leading to undefined behavior. The code concludes by printing the pointer's value to the debug output using std debug print. This not only demonstrates the conversion but also underscores the concept of pointer management in Zig, which is essential, especially in systems programming where performance and memory handling are paramount. Remember, handling pointers and their conversions involve careful consideration of memory validity to ensure safe and correct program execution. Now let's see how we can implement a function to convert a pointer back into an integer address. In this code, we begin by declaring an integer variable value and initializing it with the number 42. This variable will allow us to experiment with pointers. We then obtain a pointer to this variable using the addressive operator and value, effectively creating a pointer ptr that points to our integer. Next, we focus on converting this pointer back into an integer representation of its address using the @int from ptr function. This conversion is essential as it provides insights into memory management and debugging, allowing us to see the actual address of value in the memory. To display this integer address, we utilize std debug print, which will output the pointer's integer value to the console. This example showcases the dual capability of converting between pointers and integer addresses, empowering us with tools for deeper memory manipulation and debugging in Zig, particularly in scenarios involving low-level programming or hardware interactions. Now let's implement a code snippet that demonstrates how to utilize pointer arithmetic with an array in Zig. In this example, we define an integer array R with 5 elements. To manipulate this array using pointers, we declare a pointer ptr that points to the first element of the array. By leveraging pointer arithmetic, we can navigate through the elements of the array effectively. In the loop, we iterate from 0 to the length of the array using the index I. Within the loop, we perform pointer arithmetic by adding I to ptr, which shifts the pointer to the ith element of the array. The asterisk operator dereferences the resulting pointer, allowing us to access the value stored at that specific location. This technique provides a more efficient way to access array elements directly, making it especially useful in performance-critical applications where traditional index calculations could introduce overhead. Thus, mastery of pointer arithmetic can greatly enhance your capabilities in handling data structures effectively in Zig. Now let's take a look at how we can manipulate a structure's fields directly using pointers. In this example, we define a simple point structure that contains two fields, x and y, both of which are integers. We then create an instance of the point structure and obtain a pointer to that instance. With the pointer to the structure, we can conveniently access its fields without going through the instance itself. By dereferencing the pointer, we can read and modify both x and y directly. For example, we print the coordinates of the point before updating them. This demonstrates how effective pointer arithmetic is when managing data structures. By incrementing the x and y fields directly through the pointer, we showcase the flexibility and efficiency that pointers bring to the table. Finally, we print the updated coordinates, illustrating the changes made through the pointer. This example emphasizes the power of pointers in Zig, as they provide quick access to structure members and enable easy modifications without cumbersome syntax. This ease of manipulation can be particularly helpful when dealing with complex data types. Now let's take a look at how we can manipulate the value of a variable directly through pointers. In this example, we define a function called modifyValue, which takes a pointer to an i32 as its argument. This function dereferences the pointer and assigns a new value of 100 to the location it points to, effectively modifying the original variable. Next, we enter the main function, where we declare a variable value initialized to 42. We then create a pointer ptr that points to the address of value using the address of operator. And by invoking the modifyValue function and passing ptr, we effectively transfer ownership of access to the integer it points to. When the function completes, the variable value has been updated, and we verify this change by printing the modified value to the console. This illustrates how pointers facilitate direct modifications to variable values and highlights the concept of pointer ownership, where altering the data through a pointer reflects changes in the original variable. Now let's take a look at how to manage dynamic memory allocations safely using Zig's allocator. In this example, we begin by importing the standard library and defining the main function. We use std heap page allocator to create an allocator for memory management and define the size of the array we want to allocate. Next, we dynamically allocate an array of integers with the specified size. This allocation is performed inside a try block, which ensures that if the allocation fails, it will handle the error gracefully. After the memory is successfully allocated, we populate the array with values by using a loop that iterates over the elements. Here, we utilize a pointer to access each item directly, leveraging Zig's ability to safely dereference pointers. After filling the array with data, we print the values to demonstrate the allocation's success. Finally, we ensure proper memory management by freeing the allocated memory using allocator free. This step is crucial as it prevents memory leaks, highlighting the importance of ownership in dynamic memory handling. Zig encourages programmers to be conscientious of memory usage, promoting safe practices when working with pointers. Now let's take a look at how pointer casting can help us work with different data types seamlessly. In this example, we first declare a byte buffer filled with 8 consecutive values from 0 to 7. This buffer is of type U8, meaning each element is an unsigned 8-bit integer. We then create a pointer ptr which points to the start of our buffer. Next, we implement pointer casting with @ptrcast, converting our U8 pointer to a U32 pointer. This allows us to interpret the first 4 bytes of the buffer as a single 32-bit integer. By dereferencing int ptr, we retrieve this value, effectively treating different types of data in memory flexibly. It's vital to keep in mind that pointers must satisfy alignment requirements. Failure to do so could lead to misaligned accesses, causing runtime errors. This powerful technique showcases how Zig enables developers to manipulate memory efficiently while also reminding us to handle pointer conversions cautiously. To sum it up, we've covered a range of advanced pointer techniques in Zig that equip you with the tools necessary for effective memory manipulation. We delved into converting between integer addresses and pointers, explored pointer arithmetic, and touched upon memory ownership and dynamic allocations. Through practical examples, we highlighted how pointers can be optimized for both safety and performance. Having a strong grasp of these concepts will set a solid foundation for more complex data structures and systems programming tasks. As you continue your journey with Zig, the mastery of advanced pointer techniques will significantly enhance your programming capabilities. Happy coding, and remember to treat pointers with care.